Every day, students in a modern learning environment are constantly subjected to an overwhelming volume of simultaneous information. The prevailing assumption in instructional design is that presenting this information across multiple modalities at once caters to diverse learning styles. You see this in practice when presenters narrate their slides verbatim, or when textbooks pair a completely self-explanatory diagram with a dense paragraph describing exactly what that diagram already shows. According to cognitive load theory, combining these redundant sources of information does not reinforce retention. It actively degrades learning and transfer. The mechanism behind this failure is extraneous cognitive load. This is the mental tax generated by processing any information that is not strictly required to learn the material. Information does not have to be off-topic to create this load. Even highly relevant, topically accurate information becomes extraneous if the learner already understands the core concept. What educators intend as a helpful reinforcement actually functions as a metabolic tax that shuts down the brain's ability to learn. The reason extra modalities fail comes down to the physical mechanics of the human brain. This schematic illustrates working memory as a narrow bottleneck between our sensory input and long-term memory. It is a strictly limited buffer that can only hold a few items at a time before processing them. When you process two identical streams of data, like listening to a speaker while reading the exact same words, the brain is forced to actively cross-reference them. This cross-referencing consumes the exact same cognitive resources needed to actually understand the material. The bottleneck clogs and the data is lost. Cognitive scientists refer to this specific phenomenon as the redundancy effect. Ultimately, adding redundant modalities forces the brain to do useless clerical matching work instead of building permanent knowledge. How do we objectively know whether to integrate multiple sources of information or strip them away? We can start by looking at this geometric triangle and the separate text box of algebraic equations next to it. The text stating that angle ABC equals angle XYZ cannot be understood without referencing the visual diagram. Because these sources are dependent on each other to make sense, physically combining them reduces cognitive load. This is known as addressing the split attention effect. Contrast that with this biological diagram of blood flow. It shows a distinct path of blood moving from the left ventricle to the aorta. This diagram is fully intelligible on its own. Any accompanying text that repeats the visual data creates independent sources. When presented together, the brain instinctively tries to map the redundant text to the already understood diagram, wasting vital working memory capacity. The physical format of the media is irrelevant. The logical relationship between the sources, whether they are dependent or independent, dictates whether combining them helps or harms the learner. These exact mechanics apply directly to physical, real-world training environments, like using software manuals to operate highly complex industrial hardware. Sweller and Chandler tested this in 1994, tasking novice learners with acquiring a new technical skill. The learners were divided into two test groups. Group A used an instructional manual alongside the actual functioning hardware.
Group B used only a manual containing diagrams of the equipment. This bar chart displays the counterintuitive results. The manual-only group learned significantly faster and performed better on practical tests. For novices, the physical hardware acted as a redundant, highly distracting element that overloaded their working memory before they could understand the basics of the procedure. In early learning stages, physical reality itself can be a redundant distraction. Stripping away the hardware accelerates theoretical understanding. We see a similar mechanical failure in corporate training environments, specifically with narrated presentations. Slava Kalyuga tested this in 1999 using mechanical engineering concepts. The experiment tested three formats containing identical information: written text only, spoken text only, and written plus spoken text presented concurrently. This chart reveals a severe drop in post-test scores for the dual modality group compared to the spoken-only group. Reading and listening at the exact same time creates a cognitive echo. The brain is forced to synchronize the auditory and visual inputs rather than analyze the meaning of the data. Subjective ratings of cognitive load from the participants confirmed that the written text, intended as a helpful backup, was actually a heavy burden. Narrating a text-heavy slide does not double the learning opportunity. It actively halves the viewer's available cognitive resources. Decades of older second language studies contradict this, claiming that reading and listening simultaneously improves outcomes. This branching timeline exposes a fatal experimental design flaw in those legacy studies. They tested for short-term comprehension on the exact same material, not long-term learning transfer. In a standard comprehension test, dual modality learners score high because they simply choose to focus on whichever single modality is easiest for them to process in that moment. Rigorous testing forces learners to apply acquired schemas to entirely new, unseen material. Under those conditions, the single modality learners vastly outperform the dual modality learners. Short-term comprehension is an illusion. True instructional design must prioritize the long-term transfer of schemas, which redundancy actively prevents. The primary boundary condition that determines if the redundancy effect will trigger is element interactivity. If a topic is incredibly simple, characterized by low element interactivity, working memory isn't threatened. Redundant information won't cause measurable harm here. This matrix maps the specific danger zone where cognitive overload is guaranteed. It occurs when high interactivity combines with system-paced instruction. System-controlled pacing, like an unpausable lecture, removes the learner's ability to slow down and manage their cognitive load. Learner-controlled pacing can partially mitigate the redundancy effect by giving the brain time to clear the bottleneck before moving on. To maximize the narrow limits of working memory, audit all material ruthlessly. If a diagram explains the concept, delete the text. If you must narrate a presentation, eliminate the on-screen words. Great instructional design isn't about how much media you can add to the screen. It is about ruthlessly eliminating anything the brain doesn't strictly need to survive the bottleneck.